Welcome back again, everybody. We have a couple of topics left to discuss as far as acids and bases go before we move on. One of them happens to be what happens with polyprotic acids and bases. And polyprotic acids and bases are acids that have more than one acidic proton, having two protons that can be removed or three. Polybasic bases have more than one OH group that can be removed or generate more than one OH minus per molecule in solution. We're going to concentrate on the acids because they're more important as far as problem solving goes. So a polyprotic acid has two or more acidic protons. So we're not going to calculate any buffers with polyprotics. We're just going to work on just the acids themselves and talk about their characteristics. So with these two or more acidic protons, each one has a Ka. And the protons themselves remove sequentially. They do not both pop off the molecule at the same time. First one and then the other. Each one has an equilibrium associated with it. So the first one has the larger Ka, and the second one will have a smaller Ka. Each of these steps is a Bronsted-Lowry step. So the acid reacts with water to produce an H3O plus and a conjugate base, and if it's polyprotic, that conjugate base now is still acidic and can drop off another proton into the solution. So this can happen with strong acids or weak acids. So for example, H2SO4. H2SO4 has two acidic protons. It's an equilibrium. Well, we should put a water molecule in there, shouldn't we? It's a Bronsted-Lowry acid. That's in equilibrium with HSO4 1 minus plus H3O plus. And that equilibrium is very much favoring products. H2SO4 is a strong acid. So that equilibrium goes to completion. The second step, though, the second proton removes from bisulfate ion, HSO4 1 minus. So HSO4 1 minus plus H2O is in equilibrium with H3O plus SO4 2 minus. And that one has a Ka of 1.2 times 10 to the minus seconds. So it's still a pretty strong weak acid, but it is still a weak acid because it has a Ka much less than 1. So that's what happens for strong diprotic acids. The first proton is a strong acid, the second one is a weak. So if we look at an acid that is diprotic but weak for both protons, H2CO3, carbonic acid. It does the same sort of thing that the sulfuric acid did. The protons remove one proton at a time. So H2CO3 plus H2O in equilibrium with HCO3 1 minus plus H3O plus. This equilibrium has a Ka value of 4.3 times 10 to the minus 7th. And then our bicarbonate ion is also still acidic. So HCO3 1 minus plus H2O in equilibrium with CO3 2 minus plus H3O plus. Bicarbonate is an even weaker acid than carbonic acid. because it's the second proton being removed instead of the first. This one has a Ka value of 5.6 times 10 to the minus 11. And this is pretty common for diprotic weak acids. The Kas are significantly different from each other. It's not that you can't find one once in a while where the Kas are awfully close to each other, but typically they're significantly different in order of magnitude or greater difference in their Ka values, which leads to one of them being removed almost entirely before the second one gets removed. So that's why we call it a sequential removal of the protons. So this kind of gives you an idea of what happens with diprotic and if it was a triprotic, we'd have 3 K expressions for each acid. Each step has a Ka value. Each proton is removed sequentially. When we write out stoichiometry with triprotics and diprotics, we still have to account for those 3 protons. And after a reaction, an acid-base reaction, all 3 of the protons, or both of the protons in the case of a diprotic, have been removed. But we need to be aware that they remove sequentially when we just dissolve it in solution. All right, thanks guys.